21.6 degrees Celsius. That was the measured gap between two identical glass boxes sitting side by side in direct sun in Ningbo, China. No compressor, no fan, no wire running to either one. One box was simply wearing something you cannot see or plug in. You heard that, right? A swing that size usually means someone switched on an air conditioner. Nobody did. That is not a lab projection. It is a peer-reviewed result, and the same underlying film already coats phone glass sold today by Xiaomi and Apple. Let me tell you what that actually means in plain English. You know the feeling of an air conditioner running flat out on the worst day of summer and still losing. This was built to make that fight unnecessary, and the glass on a phone is not even the real story. And that is just the beginning. Hit a quick like and subscribe so you do not miss the next one, because by the end of this video, you will understand exactly how a sheet of glass cools an entire building without a single watt of power. For as long as buildings have had glass, keeping a room cool has come with a trade-off nobody questioned. You could block the heat or you could keep the light. Nobody found a way to get both without paying for it in electricity. For decades, the only real weapons against a hot window were tint and power. Reflective and tinted films were the industry's answer, and they worked to a point. Field studies out of Hong Kong found that a filmed window could reject as much as 30% of the sun's diffuse heat and over 50% of its direct beam radiation. That is a real number, and it saved real electricity, but it came at a cost that showed up the moment you looked through the glass. Rooms went dim. Views turned gray. Anyone who wanted a window that still felt like a window had to give up the very thing that made the film work in the first place. The other option was smarter and far more expensive. Electrochromic glass, the kind that darkens on command, could tint itself without a physical film, adjusting in real time to the sun outside. Here's the brutal catch. Every one of those panes needed a live electrical connection to function. Take away the power even for a minute, and the glass simply stopped doing its job. For over half a century, the building industry treated this as a fixed law of physics. You could have a clear window, or a cool window, or a window that needed to be wired into the grid. You could not have all three without picking a compromise. Every attempt to escape that trade-off ran into the same wall. Add a coating, and you lost the light. Add electronics, and you lost the independence from the grid. Engineers treated it the way you might treat a law of nature. Not something to be solved, just something to be managed as gracefully as possible. This is the wall that Professor Zhu Jia spent the better part of a decade trying to walk straight through. Zhu Jia leads a research group at Nanjing University's School of Sustainable Energy and Resources, and by the time most of his peers had moved on to easier, faster-funded wins, he was still chasing one specific, stubborn problem. Radiative cooling, the idea that a surface could shed its own heat directly into the night sky without consuming a single watt, was not a new concept. Physicists had understood the underlying principle for years. What nobody had managed to do was make it work in something you could actually see through. Opaque coatings on a rooftop were one thing. A transparent, durable, sellable pane of glass was another problem entirely, and it was the one Zhu Jia had committed himself to solving. His goal was never simply to prove the physics worked, it was to make radiative cooling something that could sit in a window frame, survive a summer, and never once need to be plugged in. That commitment meant years of dead ends before there was ever a headline, and headlines, when they finally came, are exactly where the story starts to turn. By 2019, Zhu Jia's team was ready to publish something the rest of the field was not prepared to take seriously. They called it a new class of material capable of regulating heat purely through radiative cooling, a surface that could stay cooler than the air around it, using nothing but the way it interacted with sunlight and infrared light. To most engineers reading the paper, this sounded like a rounding error dressed up as a discovery. Here's where the consensus broke. The same dismissal had already happened once before, a few years earlier, when the first daytime radiative cooling coatings appeared. Those early materials worked technically, but only on rooftops and only because they were opaque. Engineers at the time called them a laboratory curiosity with no realistic path to a real product. They were wrong. Those same non-transparent coatings are now a standard cooling treatment on warehouse roofs across Asia, quietly cutting air conditioning loads on buildings nobody thinks twice about. Zhu Jia's team was proposing something harder. Not a coating for a roof nobody looks at, but a material that could work on glass. The one surface in a building that has to stay transparent to be useful at all. International reaction to the 2019 paper was polite skepticism at best. Radiative cooling had a reputation as a physics demonstration, not an industrial material. Making it transparent, durable, and cheap enough to manufacture at scale sounded, to most of the field, like solving 3 unrelated problems at once. Here is what most people get wrong about breakthroughs like this one. They assume a paper is the finish line. For Zhu Jia's team, the 2019 publication was the starting gun. The actual program that followed involved years of testing which molecular structures could selectively block the sun's visible and near-infrared energy while still emitting heat efficiently through a very specific, very narrow window in the atmosphere. Nobody outside the lab believed this would ever leave a bench. Funding for that follow-up work was not guaranteed. A team chasing a problem the rest of the field considered solved or unsolvable does not attract easy support. Zhu Jia's group kept going anyway, treating the 2019 paper as proof of concept rather than proof of a product. But this is only the beginning of the challenge, not the end of it. What came next made a published paper look like a footnote. Here is the part that changes everything. The physics behind all of this was not new. Scientists had known for decades that Earth's atmosphere has a narrow gap between 8 and 13 microns, where infrared light passes almost straight through into space instead of bouncing back down and warming the air. Picture a soundproof wall with exactly one crack running through it, tuned to a single frequency. Every other sound gets absorbed. That one frequency slips through untouched, all the way out. Heat emitted at the right wavelength behaves the same way. It does not warm the sky above a building, it escapes it entirely. This was the exact gap Zhu Jia had been circling for years. Not the idea that radiative cooling worked. That part was settled science. But the idea that you could engineer a material thin enough, clear enough, and durable enough to use this atmospheric gap on an actual pane of glass, rather than a slab of rooftop paint. A surface engineered to emit strongly in that 8 to 13 micron window sheds its own heat directly into space, night or day, without ever warming the surrounding air. That is not a coating that blocks heat. That is a coating that removes it. Early lab results confirmed the underlying principle worked exactly as the physics predicted. Prototype surfaces measured consistently cooler than ambient air under direct sun, with no power source and no moving parts of any kind. The single-sentence verdict engineers kept returning to was simple. Heat was leaving the material faster than sunlight could put it back in. Every measurement pointed the same direction. The atmospheric window was real, it was usable, and a surface tuned to it did not need daylight, darkness, wind, or any outside condition to keep working. It simply kept shedding heat hour after hour on its own. That verdict alone would have justified years of research. It was not enough to build a product. Because knowing that the atmospheric window exists is one problem. Getting a material to use it while still looking like ordinary window glass is an entirely different problem, and it is the one that almost broke the whole project. Here is the brutal catch nobody wanted to admit out loud. Any material efficient enough to emit heat strongly in the infrared tends to also absorb visible light, which means it looks tinted, cloudy, or outright opaque. A transparent, colorless material, by contrast, is usually infrared lazy, letting heat pass right back through instead of radiating it away. Zhu Jia's team was chasing a material that had to do both at once: reject the sun's visible and near-infrared energy, stay optically clear to the human eye, and emit strongly in a completely different part of the spectrum, all in a layer thinner than a human hair. It sounds like it should not work. That is exactly why it does. Getting there meant risking a chemistry pathway most of the industry had abandoned. Associate Professor Zhu, working alongside Zhu Jia, later described the challenge as an impossible triangle: performance, stability, and affordability, with every gain in one dragging down the other two. What the lab expected to take 2 months stretched into 6, as engineered layers that performed beautifully on a bench kept failing the moment real manufacturing tolerances were applied. Early production yields sat around 50%, meaning half of every batch produced was unusable. The team's answer was not a single fix. It was dozens of small ones, adjusting formulations and automation together until yield climbed past 90%. The first place the material proved itself commercially was unexpectedly a smartphone. Bonded onto phone glass, the film dropped internal temperatures by 5 to 10 degrees Celsius and improved thermal efficiency and reliability by as much as 40%, enough that Xiaomi and Apple both adopted it for production devices. That yield climb from 50 to over 90% was not a footnote. It was the difference between a laboratory curiosity and something a factory could actually afford to produce at volume, batch after batch, without throwing half of it away. A phone screen, though, is a few square inches. A building is thousands of square feet, facing wind, rain, seasons, and years of direct sun the glass on a phone will never see. Now here's the part that puts everything into perspective. Scaling this from a phone screen to a building is not the same problem solved bigger. It is a different problem entirely. Moguang New Energy, the company Zhu Jia's team launched in 2022 with backing from Nanjing University and the Suzhou High-Tech Zone, runs automated production lines where tempered glass passes through ion beam deposition chambers, building the cooling film up one atomic layer at a time. A phone only has to survive a pocket. A window has to survive 4 seasons, every compass orientation, and years of direct exposure without losing its optical clarity or its cooling performance. To prove the material could handle that, researchers ran a field study in Ningbo, China, placing 2 identical test enclosures side by side in direct summer sun. One fitted with the transparent radiative cooling film, one without. The measured gap between them reached 21.6 degrees Celsius at peak sun. That result was significant enough that engineers extended the validated model using Energy Plus building simulation software to an 815.1 square meter glazed exhibition building. The kind of structure, malls, libraries, stadiums, where glass dominates the exterior and air conditioning bills dominate the budget. The most extreme proof of scale came from somewhere no building code ever anticipated. Since 2022, Moguang has applied the same underlying radiative cooling technology to glacier preservation work on Dagu Glacier in Sichuan Province, reporting an 80% reduction in melting across pilot areas. A material engineered for a phone screen is now shielding a glacier. The part nobody covers is how directly that connects back to a window. The same infrared physics doing the work on ice is doing the work on glass. The glass essentially performs the job of a thermostat with no thermostat attached, no sensor, no controller, no signal, just a surface that behaves the same way every hour of every day it is exposed to sky. There is nothing to fail because there is nothing running at all. That is the entire point of the design and why it holds up for years. 4 smartphone brands now use some version of this film, and the company behind it has expanded well past electronics into building coatings, cold chain logistics, and solar applications, each one testing the same underlying physics against a different set of demands. A result that large, across that many surfaces, needed independent confirmation before anyone in the industry would trust it. Here's the honest picture. Independent, peer-reviewed research, separate from Moguang's own commercial data, backs the building scale claim. A team from Zhengzhou University, working with the University of South Australia, published results in Cell Reports Physical Science, projecting that a transparent radiative cooling film could cut a building's annual energy consumption by up to 20% in hot climates, purely through reduced air conditioning load. Translated into human terms, that is a full season of an air conditioner working meaningfully less hard on a bill that shows up every single month in a city where summer heat is not an inconvenience, but a recurring emergency for the power grid. Multiply that across an entire block of glazed buildings, and the savings stop being personal and start being municipal. Here is the honest trade-off, and it matters. This technology is not universally beneficial. Comparative studies show radiative cooling films deliver strong cooling season savings in hot cities like Guangzhou, while in cold cities like Harbin, the same film can modestly increase winter heating loads because a surface built to shed heat all day does not know to stop once the temperature drops. This is not a flaw hidden from the record. It is a limitation engineers openly acknowledge, and it is exactly why deployment strategy matters as much as the material itself. Engineers who work in this field will tell you that acknowledging a limitation like this one is not a weakness in the pitch. It is what separates a durable industrial material from a piece of marketing. That caveat does not undo the headline. A sheet of glass, engineered correctly, measurably cools a building without consuming a single watt of electricity to do it. For Zhu Jia, that sentence is the answer to a question he had been chasing for over a decade. Not whether radiative cooling worked, but whether it could ever leave the lab and become something ordinary, sellable, and real. It has. Moguang now expects total revenue north of 100 million yuan this year, with tens of millions of that already coming from building coatings, cold chain logistics, and solar applications beyond the original smartphone deal. If a phone that runs 5 to 10 degrees cooler surprised you, the building scale version of this is going to be even harder to believe once it reaches your own city. Hit subscribe so you're there when it does. Zoom out from one building and the number that matters is not 20%. It is 20. According to the International Energy Agency, air conditioning and electric fans already account for roughly 1/5 of all electricity used in buildings worldwide, and without a change in course, global energy demand for space cooling is set to more than triple by 2050, consuming as much electricity as all of China and India combined use today. That is the real audience for this technology, and it is not one country. It is every sector where glass and heat collide at scale. Commercial construction, retail, cold chain logistics, keeping food and medicine stable in transit, and now textiles, as sun protective fabric using the same underlying material moves toward mass production. Each of those sectors is fighting the same rising electricity curve in a hotter world with a grid that was not built to absorb it. The engineering advantage here is genuinely difficult to replicate, and not because of a patent filing. It is difficult because getting a material to be simultaneously transparent, durable, and radiatively efficient took a decade of failed formulations before it worked even once. Adoption will not be instant. Retrofitting existing glazing supply chains, tuning formulations to local climates, and managing the cold climate trade-off all take real time and real capital. Industry response so far has been cautious optimism rather than a rush, the kind of pattern that shows up whenever a genuinely new material threatens an existing comfortable status quo. None of that caution is unreasonable. Glazing manufacturers operate on decades-long product cycles, and nobody swaps out a supply chain overnight just because a peer-reviewed study looks promising. The genuine advantage here has to prove itself building by building, climate by climate, contract by contract, before it becomes the default rather than the exception in new construction anywhere in the world. They said the same thing about solar power in the 1970s. Photovoltaic panels cost roughly $100 per watt, dismissed by most of the energy industry as a spacecraft-only novelty with no path to mainstream use. That price has since fallen more than 99% to well under 30 cents per watt, and solar is now among the cheapest sources of new electricity generation anywhere in the world. The limit on radiative cooling glass, like the limit on solar decades ago, was never political. It was technical, and technical limits are the ones engineering eventually solves. If you have been following this channel's look at China's materials engineering breakthroughs, this is very much the same pattern at work. A problem physics allowed and manufacturing finally caught up to. If you made it this far, you now understand more about how a window can outcool an air conditioner than most people who write about climate technology for a living. Here is what was actually proven. A material can be engineered to stay optically clear while emitting heat directly into space through a narrow gap in Earth's own atmosphere, and that material can be manufactured reliably enough to sit on a smartphone, a warehouse roof, a glacier, and eventually the windows of an ordinary building, all without a single watt of electricity keeping it running. That is not an incremental improvement on air conditioning. That is a different category of solution entirely, one that works precisely because it asks nothing of the power grid at all, and that is exactly why it scales the way it has, from a single lab bench to buildings and glaciers alike. The largest implication is not a phone that runs cooler, or even a building that saves 20% on its cooling bill. It is a genuine dent in a problem the entire world is currently losing to. A warming planet demanding more and more electricity just to stay livable indoors, in a century where every gigawatt not spent on air conditioning is a gigawatt available for something else entirely. Multiply that 20% across every glazed building in every hot city on the planet, and the number stops being a single building's utility bill. It becomes a meaningful bend in a curve the International Energy Agency has been warning about for years, a curve that was heading straight up until a material like this one gave it somewhere else to go. For Zhu Jia, a decade of chasing a problem most of his field considered unsolvable now sits quietly in glass, on buildings, on phones, and on the surface of a retreating glacier. That is not a small footnote to his career. It is the whole point of it, finally realized. If this changed how you think about what a window can actually do, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Should governments require radiative cooling glazing in new construction to fight rising cooling demand? Or should this stay a market-driven choice left entirely to builders and buyers? I read every single one of them. See you in the next one.